That's flow attachment, when the flow is attached to the surface. Now, the flow separation phenomena, or when the flow separation happen, what are those conditions? Now, thing is, here we can see the flow is attached to the surface, means the no slip condition, or what we can say is the velocity of fluid at these places are zero. Okay, at these places are zero, at these places they are zero. On the top it is increasing. Now in this case the pressure is decreasing. Now if we can increase the pressure locally, if we can increase the pressure locally, in fact over here the reversal will happen, because the fluid particles which are near the surface, they will try to retard. They are trying to retard, they are retarding. Okay, the velocity is decreasing, but as the pressure is increasing, okay, so at this area the pressure is increasing, and at this area the pressure is decreasing, and that creates a coupling. And we know the pressure, the flow, from the Bernoulli's principle, the flow will happen from high pressure to low pressure. So basically at this area we have a high pressure, and at this area we have a low pressure, so the coupling will happen. And because the velocity vectors, they have the velocity, the fluid particles, they have no the viscosity, so they will try to stick the surface. But because of the Bernoulli's equation, or because of the flow coupling, the flow will start leaving the surface from here. Now this is the phenomena which is called the flow separation, or adverse pressure gradient. At this stage the flow will start leaving the surface, which is very important. So in this case, we have seen how the flow will be attached to the surface. It will not leave the surface. And in this case, the flow will start leaving the surface. So if we see the D point, which is near the surface, and C point, which is just below, just above the surface, and the B point, which is, at somewhere here near the boundary, and A is the free stream over here. So we can see at the C point where flow is retardation is happening over here, and the B point where the flow is accelerating, because it has to follow the conservation law. In fact, the Bernoulli's principle is not applicable when the flow separation is happening. So that's how the flow separation happens, because of the viscosity, because of the no slip condition, because of the change in the pressure. So let's see an example of how the flow separation happens, and how it is important into what I would say, into the industry or in reality. Now here we see we have a wing airfoil, okay, and by changing the angle of attack, we can see the flow separation, or the flow disturbance is happening on the rear side. Now at this case, now the flow separation is not happening, or the flow separation is not happening in this case. Now when we are changing the angle of attack, we can see at this area, the flow is not at all. Now let me pause the video, sorry. Let me pause the video where we can now. Yeah, so we can see at these places the flow is attached. The flow is attached to the surface, and on the top the flow is attached to the surface. But at this area, the flow is not at all attached. That's called the flow separation from the body. And you can see the effect of flow separation, that it is creating a lot of disturbance in the flow, where we can see it is not at all stable. It is changing drastically. So let's see once more. So we have seen how the flow separation happens when the flow is not attached to the body. But the effect of flow separation is really, it can create a lot of issues. We have seen when the airfoil was 0 degree angle of attack, the flow was pretty much smooth. The downstream flow was very smooth, in fact. But as the angle of attack was changing, we were seeing there is a huge disturbance on the backside of the airfoil. Now, one thing is, if anything is behind that airfoil. If anything, if any object is behind that airfoil, in the case where the airfoil has a 0-degree angle of attack, uh, that object which is behind it might not have that much effect. But as you know, the angle of attack is changing, there will be huge disturbance. There will be a huge disturbance on the object which is behind the airfoil, and those effect can be drastic, those effect can be positive, those effect can be negative also. So let's try to see an example of an automobile and try to understand what is the effect of flow separation on that. So let's see, we have a car. Okay, so on the front, we know, I'm not going to explain the physics of this car, but I'll try to make you understand how flow separation is important in this car. So let's say if it is running at very high speed, same as the airflow, the airfoil. So we will have a high pressure in the front of car, because stagnation pressure, because the car is moving, and then the geometry of vehicle is like that when the flow is interacting with the car, it will try to stop the car restriction of the air. So here at the front of the car, the pressure will be maximum, and as the flow is moving along the car, the pressure will change, the velocity will change. Now I'm not telling whether it will be high or low, because I'm not interested in all. What I'm interested into is the flow is attached to this surface, and slowly when we see later on, when we see that the flow, as soon as it is moving from the front to back, at this areas where you can see the cursor, it is not filled. At this area where you see it is not filled, that means the flow is separated. I'm not going to explain the physics why flow separation happens, but I want to make understand what is the effect of flow separation on that. So from A to B, I would say the flow was attached to the car. From B to C, the flow was attached to the car. From C to D, in fact, the flow was attached to the car. But from D to E and further after, the flow is not at all attached to the car. That should have some negative or positive effect. I don't know. So let's see what are those effects. Now, the movement of car is happening from left to right. Sorry, right to left. Okay, and if we take the steady state, that okay, wind is not moving, wind is stationary, we are moving the car, so the car is moving from right to left, and it is creating a disturbance into the air, or air is creating a restriction of the movement of car. Okay, now the thing is, we have a high pressure in the front of car and we have a low pressure at the back of car. How? Because the when the flow separation happens, when the flow is not able to attach to the car, that's a low pressure where anyway, I mean, not in that way. If I can simply explain you, the car is interacting with the air, so at this place the pressure will be higher because the air is trying to stop the car. So at this place, stagnation pressure or the maximum pressure will be there here. At this place, because air is not at all interacting, at these places. So of course, on the rear side of car, the pressure will be lower than what is at the front of car. That's what I can say. Okay, the flow separation, the low pressure is one of the phenomena or one of the outcome of the flow separation. But that's not where I'm going to, not my area of interest. Okay, now, as per Bernoulli's equation, the flow should happen from high pressure to low pressure. Now you see there are two forces which are very much opposite. As per the principle, the flow should happen from high pressure to low pressure. So from left to right. But because the car is accelerating and it is burning fuel, it is creating a pressure. It is creating, the power. So the movement happens from right to left. Okay. Now, when we calculate the drag force of car, we include skin friction drag and form drag, which is called the pressure drag. Now, this difference of pressure is going to play a major role. This difference of pressure. Now, try to understand, the more flow separation, the more low pressure area, and the more form drag or the pressure drag. If we just take, or if we just consider the pressure at point A and pressure at point C, the pressure at point A will be always higher. Now, the thing is, what we can do is to minimize the difference between A and C, because that is directly proportional to the fuel what you're burning, and that's equally, proportional to the mileage of car, or the fuel economy of the car. Now those things will totally depend on, of course, the fuel consumption, as I said, the vehicle design, that's more important. Now the vehicle design should be like that there should not be the higher flow separation, minimize, and of course the vehicle performance. So the flow separation, if we talk little bit more in details, the flow is interacting with the surface of car at this point where maybe the geometry of car or the velocity of car is really high, due to which the separation happens. Separation doesn't happen just because of the pressure gradient. That is one thing how you can measure, but of course the geometry plays a major role in the flow separation phenomena also. So in this case we can see we have almost curvature over, then we have a slant, we have 90 degrees slant. So the air which is interacting at this places, it's not able to fill the space which is behind the car. That's non-technical way of saying that you have a low pressure over there. So that's one place where you can see the application of flow separation is very much very much important when you're taking the fuel consumption of car. This is same kind of principle can be applied to F1 trucks, buses, any automobile if you take. In fact, the aircraft also, but aircraft little bit the physics is little bit different. There you want more lift and less drag, so that's one different, but the phenomena or the principle remains same across whether it's aerospace or automobile, it's remains same. So that's the reason why we have seen Lamborghinis are more sleek, Lamborghinis, and the high speeds car where they are really aerodynamic design, where the flow interaction or the flow separation should be the normal. And SUVs, there is one more reason for SUVs which have the low fuel economy, not big just because of the vehicle structure, but because of the vehicle design also. Now one more thing is example of flow separation is in SUVs. We have seen the rear windscreen is always dirty, or sometimes it is very dirty because that's the reason of the flow separation over here. Now this low pressure area is only near the car, only near the car, okay, only near the car where interaction is happening. But in ambient, the pressure is much more higher, the pressure is higher, that's 100% sure. Now I cannot give evidence as of now, but the pressure the pressure which is just behind the car is a bit lower than the pressure which is near the ambient. So of course again the flow from the Bernoulli's principle from high pressure to low pressure. Now in reality, when car is going on the road, there are dust particles, there are sand. So that's the reason why you see sometimes that even the sedans or the hatchback also, the rear windscreens are pretty much dirty if you go into a dusty place, if you go into the places where the roads are not very clean, or if it is windy. That's one more thing, and that's the drawback of the flow separation of the car. It's not just the fuel consumption, but also the vehicle soiling also. Okay, so that's one thing what we have seen. Now next, let's talk about something which is called the type of flow, where we categorize. That's more important when you are trying to understand the computational simulation. Now all these things are still not related to any tool. All these things are related to the phenomena. All these things are related to the physics. We haven't spoke about anything about the tool, neither ANSYS, Fluent, or anything. This is all what we are trying to understand is independent of tool, the physics and certain laws, or how we can understand first the fluid dynamics. Later on we can see the computational fluid dynamics. Now I'm not going into the detail of what is laminar flow and turbulent flow, but in fact I'm more interested into what's inside the turbulent flow. What's what is how turbulent flow is very critical to handle. So I'm not talking much about the laminar flow. Laminar flow is it's very simple, that low velocity flow, and the velocity vector are quite parallel and stable, and that gives you pretty much stable results. Now challenging part in computational fluid dynamics, the most challenging part in computational fluid dynamics comes when you start dealing with turbulent flow. It's not like I'm saying laminar is, less challenging. No, the expectation with the laminar flows are well established that, okay, this is the flow and that's how the result should be. And a lot of experiments have, we have seen that we have a good correlation between experimental and the computational domain. Now, the most important the most complex part in the computational simulation comes when you are dealing with the turbulent flow. Now, the turbulent flow, what I can say is, uh, the heights of randomness, or the degree of randomness, whatever you can think, imagine, that's a turbulent flow in the fluid when the fluid is moving. So we can see, like, it's really complex. It's not at all, the fluid layers are not moving parallel, they're crisscross, they're jumping here and there. So the velocity vectors, where you can see near the wall, it is somewhere here, and all of a sudden they're jumping from here to here. It's highly unstable. You cannot assume, you cannot predict what's exactly happening if the fluid particle is happening from here to here. Of course, it is taking the energy from here to here, so the mixing is also good. But this usually happens at this usually happens at high velocity, not at the low velocity. That disturbance need to have some kind of energy which you need to bring into the flow. Now, boundary layer, we have seen the boundary layer thickness. The boundary layer thickness, we have seen that it's the effect of the wall, or the effect of the, the roughness of the wall, up to which extent. So that's what is called the thickness, or the boundary layer thickness. So let's see what is inside the, the boundary layer, what exactly is inside the boundary layer. Sorry. So in laminar boundary layer, we have viscous layer, which is usually, very much established, or what you can say, in the disciplined fashion. But in turbulent boundary layer, which is divided into, you are seeing now the viscous sublayer, and then we have a buffer layer, we have a turbulent region. That's where all the physics, that's where all the challenge, that's where all the the randomness, or the expectation, or the physics change happens, and that's the place where the most challenging part occur. Now let's see how exactly, what exactly is inside the boundary layer. So if we have a wall over here, we have then sublayer. Okay, I'm not much interested into what exactly the layer is called, but I'm trying to make you understand what exactly those layers are. Now, the fluid layer, which is exactly on the wall, or very near to the wall, the next to the wall, that will have a laminar flow. Okay, because that's highly viscous, that's very high viscous flow, and the randomness will be very less. It will be very stable because it will stick to the surface. Now, the reason behind that is because it will have a maximum effect of wall. The wall will try to grab it, the wall will try to stop it, but because of the inertia, because of the flow, because of the difference in the pressure, or because of the external force, the flow is moving over the wall. So here the inertia, in fact, is what you say, is still dominant because the fluid is able to move, but still the viscous forces are dominant enough to slow it down. Okay, so that's the place where there will not be any fluctuation. In fact, the fluctuation will be very low, and that's the place where the flow will be pure laminar. But that's the place where the shear stress would be the maximum, where the skin friction would be the maximum, where the interaction of the wall with the flow is maximum, where the effect of wall and the fluid interaction is maximum. Now, understood. As we are moving away from the wall, there will be a region where we have a collaboration of a free stream, which is what you say is unaffected by the wall, and the effect of the wall. So it's kind of mixed region where you have both region. still the free stream is still, one of them is, I would not say dominant, but it's kind of mixed feeling, where the turbulent is not maximum, where the wall function is not maximum. It's kind of, okay, let's share it properly, but it's still it has less effect of wall in this region. So in total, this is called the inner region, where you have effect of wall, means dominant. This log layer or the turbulent layer, it has some effect, but still it's not fully turbulent. It has some randomness, you can see in the plot, but it's not that turbulent as a free stream or the outer layer. Now the outer layer is something which is dominant, which is dominant by the fully turbulent. It doesn't, the outer layer doesn't have much effect. I would say the outer layer has minimal effect on the wall. The free stream is something which doesn't have any effect of wall. That's why it could be the turbulent, I don't know. I'm not interested into what's happening on the free stream, but this is the region where the boundary layer has effect, or the, I would say, the effect of viscous forces, or the wall, the interaction of fluid with the wall has some effect. So these are the places where the physics changes randomly, the exchange of momentum, the exchange of properties, the exchange of physical parameters happens. That's the place where the physics is more drastic, and it's really hard to understand and predict. So the flow regime, we have a free stream, okay, over here, and then we have a turbulent boundary layer, and then of course in the turbulent, again we are subdividing into all these categories. Now what's happening in fact in the turbulent boundary layer, if we are trying to understand on, I'm not going to read all these the text. The thing is, when we are doing the simulation, why we need to understand all these layers or all these sub layers, because when we are doing the simulation, when we are converting the computational, when we are converting the real problem, the flow over a plate, the flow over a cylinder, the flow over a vehicle, we need to understand what kind of result you want. Remember pizza theory? So what type of output you want means what type of flow region you want to resolve. You want to resolve this one, you want to resolve the log layer, you want to resolve the outer layer, or you are not at all interested what's happening in the boundary layer. I want to just see the free stream, how the interaction of fluid is happening, but I'm not at all interested into this. Now the thing is, every layer has its own significance. Every layer has its own significance and the correlation with the result. Say for example, if I want to calculate the drag coefficient of vehicle, I will be interested into sublayer and buffer layer. Question is why and how. The first thing is, when you want to calculate the drag coefficient of vehicle, that means you are interested into two things. One thing is pressure, the variation, the pressure drag or the form drag. The second thing is skin friction drag. Now, skin friction drag is maximum at the wall, where the fluid interaction is happening, where the fluid interaction is happening with the wall, where the fluid interaction is happening with the surface, because that's the place where the friction will be high, where the viscosity will be high, where the shear stress will be high. Most important part. So what I will do, I will search, if I want to calculate the drag coefficient of vehicle, okay, I need to concentrate on this layer. Again, remember the pizza theory. What is your requirement? My requirement is drag coefficient, first thing. Second thing is, with that correlation, what I understood, I have to consider the buffer layer or sublayer. With those things, you will be able to understand the setting of solver, the setting of pre-processing, the setting of the input parameter, the setting of the parameters which are directly related to the solver, the type of solver, whether you want K epsilon, K omega SST, or you want LES. That's where is the the key point, that you need to understand all these layers properly. If you're not able to understand, if you want a drag coefficient of the vehicle and you're solving for the free stream, you're not at all going to get the correct drag coefficient. Second thing, the meshing. Let me go to the next slide. There is some parameter which is called y plus. I'm not going to explain the y plus, but yes, the y plus is directly related to the the mesh resolution, the boundary, the flow, the flow regions. So you can see over here, we are not going to explain it, but still, input parameters. So y plus is something which you do hand calculations to get some value which is directly related to the Reynolds number. I have a slide where I will show the flow process, the CFD process, where how the y plus is important. So in fact, if you're not aware of y plus, you can understand that there is one parameter which is called y plus when you are dealing with a turbulent flow. So I said y plus turbulent flow. So directly when I am saying turbulent flow, so you should get this idea that turbulent flow have all these things. So all regions where I need to get what I am solving. So we can just understand that there is some parameter which has some limitations, which has some categories, that if it is in this range, I am concentrating on this range. If it is some different range, I am concentrating. Now all these parameters are directly related to the meshing. This is what I have, the grids what I am showing is basically a structured mesh what I am showing here. So you see the near wall, you have a fine mesh, and after the wall, we away from the wall, we have coarse mesh. So it's not like you are starting from like this. No, it means if you are concentrating near the wall, you have to have fine mesh, or you have to have a good mesh to resolve everything. And if you are away from the wall, you have to have a coarse mesh. Now the reason is because the energy dissipation or the flux of energy, all these things near the surface is really typical, really hard to simulate, really changing drastically. So all these things we need to resolve properly, and that's the reason there are certain rules when you are following, when you are solving the turbulent flow. If you are not able to understand the turbulent flow properly, you will not be able to resolve the physics, or you will not be able to get the correct understanding or the correct results properly. See a boundary layer example. So this is a typical, what I can say is example of a mesh where we have seen, this is a body where we have generated the boundary layers. In fact, now these boundary layers, you see there is some variation. That's basically a rule of meshing. Again, if we try to understand that, we need to understand the whole meshing process, but that's to capture the physics properly. Now, if anyone gives me this picture and ask me what type of simulation you're going to do perform on this, the first thing is I will quickly understand, because there are boundary layer simulation. There are boundary layers. In fact, the first thing I understand is they are interested into what's happening near the wall or what's happening near the surface. That means coefficient of friction, or maybe the drag coefficient. So you're trying to simulate the shear stress near the wall. It could be, the heat transfer also. Now the heat transfer, why I said it's more important, because that's the reason where the heat transfer will be the maximum. That's one advantage of understanding the boundary layers theory. This is one place when you are fixing, sorry, not fixing, mixing the flow with the thermal simulation, because that's the place where the flow, where the fluid and solid interaction is happening, and that's the place which will where the interface of the solid and the fluid is there. So that's the place where the maximum heat transfer or the heat transfer will be important from one phase of fluid, one phase to another phase. So this is a kind of example where we can see the just seeing the boundary layers or just seeing the mesh, you can understand what type of physics we are interested into. In lot of what I can say, a lot of interviews or a lot of exams, what can be done is I can give you the screenshot like this, and I can ask you what type of physics are expected. So I can give you option, okay, drag coefficient of the body, the flow patterns and all these things. So to understand that, we have to have understanding of the boundary layer theory or the boundary layers. Now, pre-processing is something which I was talking about, and I said it's not straightforward. It's not just meshing. That's really true. The pre-processing part is something which is related to the geometry preparation, and geometry preparation doesn't mean just to work on the CAD tool. The first thing is you try to understand what is the aim of a study. It's a pipe flow, that means internal flow. It's an external flow, a drag prediction, flow separation. What exactly you're looking for? That's a part of pre-processing. That's an understanding of pre-processing. Now, what kind of physics is involved? Now, as I said, are you interested into the drag coefficient of vehicle? Are you interested into the conjugate heat transfer modeling? So why I'm always saying that, the pre-processing is a part of, all these things are part of pre-processing, because you will understand which type of physics are involved. Say, for example, on the basis of second point, if I say what type of physics is involved, if I say, okay, what I want to do is I want to do a conjugate heat transfer, or simply I want to say that I want to see the heat transfer of a block, a solid block, into the fluid. Okay. And there is some external source of air which is cooling. So in all total, it makes a forced convection where we have a heated block, or we have a block which has a high temperature. Now the important thing is, what do you understand from those parameters, or what do you understand from the physics? Second thing is, once you understand the physics, write down all the important parameters involved into that. That means the temperature difference. When there is a block, there is a solid, that means there is some material, there is, the conduction heat transfer, the convection heat transfer. So the first thing you can understand is all the important parameters which are involved into that, so that during simulation you should not miss any of the parameters. If heat transfer is involved, if a solid is involved, what is the material? Material plays an important role because of the conductivity, because of the specific heat. Convection plays an important role, because if it is forced convection, what is the inlet velocity? How much heat transfer coefficient is, what is the temperature difference, what is the area? All these factors are more important, and those comes under the part of pre-processing, where what you can do is write down all the important formulas or governing equations, so that you will be able to understand what are the important parameters when you are setting up the case. You should not miss, you should not miss. That's the important thing, why you should always understand the pre-processing part. It's not just the geometry preparation, it's something which is independent of tool. Then, of course, you need to understand the flow is laminar or turbulent, appropriate calculation, the hand calculation I was talking about. Try to understand what is a Reynolds number. Reynolds number will give you understanding, okay, whether it's a laminar or turbulent flow. If it's a turbulent flow, what is the y plus value, where you are interested, what is the physics you want to resolve or you want to solve. So those are the parameters, or that's the place. Till I would say, till this place, it is independent of any tool. This makes understanding how much you understood the problem. Lot of places or lot of interviews, they don't ask anything if you're expert in the fluent. No, I'm not at all interested if you're good into the tool and all. Tool is a way where you can set up the problem, but only thing is, how will you know all the important parameters? How will you know which physics is important? How will you know which areas I need to focus on, which is the sensitive area? If you're solving a problem which is related to the conduction, and you're not considering the heat transfer, the conductivity, heat transfer, the coefficient, so conductive heat transfer coefficient. So it might you don't have a good understanding of the physics. So that's the reason, till here I would say, you need to understand the physics first. Tool comes later, because tool is something where you're going to enable you, where you're going to put all these parameters. Now from here it starts. Okay, clean up the CAD, close unwanted holes, cracks, gaps, missing surface, all these things, domain definition, all these things are are you capturing the geometry precisely? Those things are related to the tools, which is what you can say is a part of pre-processing, but that's after understanding the physics. Now in the pre-processing also, something which is related to the mesh. We are not going into the detail of meshing, because that's totally different, in fact a big area. But important part is how you're going to choose the right element size, which is also related to the physics. If you need to understand the size of element, it should not be random. There is a logic behind how you're choosing the size of element to do the meshing. Now let's take an example of, I'll give you a background of why meshing is important. Okay, in fact I will not say meshing. I will try to show a process. I will try to make you understand what exactly happens in computational fluid dynamics, or what exactly how the flow problems are solved. So let's see. Let's say if I have a domain which is which has certain dimension. I'm not at all interested into what dimension is. It has some finite dimensions. So I have a inlet velocity v1 and outlet velocity v2. So Bernoulli's principle says, of course, the velocity v1 will be higher than velocity v2. Okay. Now I have a point A in the domain. I have velocity v1 at the inlet and velocity v2 at the outlet. So if I want to calculate, or if I want to understand what is the velocity at point A, of course, this is a constant velocity. This is a constant velocity. The velocity variation is the constant. There is no disturbance in that. So I would say somehow I will get the result something like this at this point. Maybe, I don't know, but I would say it's a linear. I'm not interested whether it's a it's different or not, but I would say at this point, from the initial at the 0 to at the L, where the v2 will be higher. So at this point, the velocity at point A, at this situation, the velocity at point B would be linear. Now the thing is, here we are able to understand, or we are able to do a hand calculation of velocity at point A easily. What we can do is, we can simply calculate the with some correlation, with some formula. With any formula we can understand the what is exactly a velocity at point A. But what if I insert the object in this, and now I want to study what is the difference in the velocity at point A will come. Now what will happen, in fact, what will happen now, the flow is hitting this area, so now this object, and there will be the velocity here, it will not be linear at all. That's one thing I understood. That's one thing I can make sure, because the velocity vectors at this place will not be linear, because here logically the flow is hitting here, so there will be some velocity disturbance, or there will be flow disturbance behind the object. Now if I want to understand the velocity, what is the velocity at point A, what I need to do is, I need to calculate the velocities at these points, at somewhere around these points, near these points, and then I'll be able to understand, okay, how much velocity is the at point A when the object is inserted. Now what, in that case, maybe the velocity something, it will come like this. So you're not sure, if you are seeing what is the disturbance, because of the disturbance how much velocity is varying, we are not sure whether it will be linear or not. Now what I did to get the velocity at point A, I splitted the domain. Okay, and what I did, in technical terms, I discretize the domain. I discretize, we have where we have a certain, this is finite distance and x in x and y direction. Now the thing is, this is a finite domain, this is very small domain. Okay, so if I want to do hand calculations, in fact I can do. But what if this domain is really large? If this domain is really big, the hand calculations is not at all possible. So what we do is, in computational dynamics or computational fluid dynamics, the same way split the domain, and the reason to splitting the domain is the same, to understand the, to get the velocity or any physical quantity parameters, flow velocity, flow, the velocity, or the pressure variation we want to understand at some point. So that's what is the background of meshing. That's what is the reason of meshing. Now I did was structured, there are again the variation in the meshing, so that's where we are not interested, but that's the reason of splitting the domain. Now if I want to if I want to get the velocities at different points, so I have to have what if I want the velocity at the middle of this square, or the rectangle. So I need to again split this, so that the variation or the point should lie on that, like this, it is lying on the node. That's the reason we need to do meshing, and that's the the background of splitting the domain. Now let's take an example where we have a car, and the meshing has been done on this car. Now the important thing during the meshing, when we are doing the meshing, are capturing all the inputs in the mesh, in the domain precisely, because see, computational fluid dynamics is something, we are simulating a body, or we are doing a virtual test of a finite domain. We have to have a mesh in a finite domain. We cannot have a mesh in, infinite domain. We have to have, boundaries in which we are simulating. So we have to have the conditions which we are defining, that is the inlet, outlet, and sidewall. That's basically the boundary conditions. But the important part is how well we are capturing the body. That's the area of interest, not this part, not here, not here, not here. That's the area of interest. How we are capturing that and how the mesh transition is happening, that comes into the meshing techniques. But that's how a mesh look like when you're going to solve a problem. Most important parameters of pre-processing in meshing is, are you able to capture the geometry properly? Now, capturing geometry properly doesn't mean you are just capturing all the edges, all the curvature properly. No, it means, are you able to retain the geometry as it is after the meshing, like the CAD? Any distortion in the CAD is happening, any variation in the CAD is happening after you're doing meshing, it should not happen. It should never happen. There are some holes and gaps which are very important into the simulation. So you need to retain that. Are you capturing those holes and gaps properly? There is some sharp edge. Are you trying to retain, or you need that? Maybe that is a critical feature of your geometry. So you have to have, or you have to capture those things properly. That comes under the meshing. Meshing is also one thing where a lot of research has been done, and a lot of research is still going on, so that you can have proper the so that you can capture the geometry more precisely and get the more important result. Because again, the mesh is the place where the flow is going to be resolved. Say for example, you are seeing this squares or rectangles at the places where you're seeing the connection. That's the places, or the center of the places, rectangles, the solver is going to solve. At the nodes it is going to solve. So the possibility is that at node A and node B, there will be a physics change. So at this point, of course, at this area, the physics is not changing drastically, but near the car, it is changing drastically. And that's the reason you need a fine meshing to capture the flow physics precisely near the body. That's why we have a fine meshing near the body, and that's why we have a coarse meshing near the away from the body. Because my interest, the area of interest for me, the simulation is the car. What is happening near the car? What is happening? What is the drag coefficient of the car? Not in fact what is happening over here. Okay. So let's go into the process. So this is what I was talking about. This is a flow chart. What can define the complexity. It's way simple. What we see, the input giving velocity, where you want to, where you are interested. The orange on the top, you're seeing it is independent of the tool. Okay, in fact the boundary layers, this is all for the understanding. The only part which is a tool is when you create or start calculating the numbers or layers, or when you start doing the meshing. So that's how it's way small. I would say it's still, I'm not able to cover this. But if you are able to understand this flow chart, if you're able to understand this flow physics, or if you're able to memorize this, you will be able to understand the CFD process at least 10 to 15%, or I would say not 10 to 15, but more than 20 to 30%. But each and every block has its own complexity. Each and every block, it has its own reasoning. But this gives you a place where you need to think, okay, step by step, what is the process? Not just meshing. What is the input? The process is, what is the input what you got, and what are the outputs you need based on that. So you need to do some calculation, you need to have some assumptions, you need to calculate some properties. So that's how I tried to summarize the CFD process, which is more or less like, okay, with this you are good to go, but still each and every block you should be able to understand properly. Now, the important part is, what we talk about CFD is something that was a background. Okay. The important part is how we are going to understand, how we are going to utilize the skills of our understanding towards computational fluid dynamics. Now here, I have one more slide for the result discussion, and let's talk about the results. This is the simulation or the velocity, u velocity magnitude, and which has been cut at the center of the body. Now you see all the cursors, they are indicating the flow under the body. And if we see sedan, we have sedan 1, sedan 2, and then we have a performance car. Performance car is something you can say sports car. And then we have a SUV, and then we have a truck. Now one thing we see, there is the geometry variations past B pillar, okay, or the, I can say, the back geometry of these cars have different. So of course what we can expect is the change or the flow behavior in the car, of course. Now the second thing is the ground clearance of these cars. SUV have a high ground clearance, crew cab truck has a ground clearance, high ground clearance, and we see how this velocity variation is happening. Now the significance of these results, or how we are going to use these results. The underbody flow in the automobile is very important. There are two reasons. In fact, one is the drag coefficient, because a lot of underbody of automobiles, all the parts are exposed to the airs, and they are very irregular in shape. There are, the axle is open, the suspension, the exhaust is there. But again, the thing is, are you trying to understand the flow physics, or you try to understand the heat transfer? Because if there is exhaust geometry on the body, there's heat transfer. You want to cool down those parts, or you are only interested into the aero part? You are only interested into the aerodynamic performance of the car. And something, we can understand that, okay, SUV is a segment. You can make a SUV aerodynamic, of course, but SUVs are something which are for all, the rough terrains, off terrain. So you need to have a high ground clearance. That's the requirement of segment. So the segment you cannot change. The truck, crew cab truck, you cannot change the segment. It has to be like this. Now the challenge comes when you have this kind of body, when you have this kind of geometry, how you can minimize the drag, how you can maximize the cooling of underbody parts, how you can, if you have a performance car, I would not allow the much air to go inside or the underbody. So that's how you can, understand the results, and that's how you can, first of all, what is the requirement of for what you were solving. So that way you will be able to understand, this is the reason I was solving. So I want to reduce the drag coefficient of the vehicle from underbody or from the upper body. Now upper body comes from the, the looks of the geometry or the looks of the car. So there you cannot do a lot of changes. You have a, what you say is, you have to compromise with the geometry. Also you have a limitations to change the upper body. Now the other part from where you can reduce the drag, maybe underbody, maybe from the wheels, maybe from the, past body, or the, what I would say is the trailing edge. So those are the parameters on which you can discuss the results. You can understand for what you ran, for what was the purpose of simulation, and what result you're getting. Now from this case, from this SUV picture, you can understand there is a lot of flow which is going underbody, and there is a huge low pressure area, or the low velocity in fact area. That is the reason, the SUV has a high drag coefficients, and in fact the trucks have much more, because again you see the slant here. This is a where this is a generating a low pressure areas over here, and then you have a more underbody flow. But one more thing is, SUVs are not a performance vehicles. They are made for, different terrains, so that they can handle off-roading. Trucks are made, these kind of trucks are made for the loading, where you can, have a passengers also, and the loading, some of the loading. So of course the segment and the limitations, but in those limitations, how good you are, how much you can help to, achieve the good quality of the product. Now in this, I would say the consumption of the fuel, or maybe the velocity, which is directly related to the geometry. So these kind of outputs you will be looking for when you're doing a simulation, which is actually important. Now again, the pizza theory, whatever output you want, you have to give all the inputs as per the requirement. That's where you need to understand the physics. That's where you need to understand the domain. If you're looking for aerodynamics of the vehicle, first you need to understand what are the important parameters in the vehicle aerodynamics. Now, second result is something which is performed by Professor Bird. This is very extensive study he has performed. In fact, I would suggest the students to go to, his page and search for his studies. He has done a lot of studies on the cyclist, on building aerodynamics, the flow near the building, the flow, the pedestrian safety. He has done a lot of work and experimental study also, and he has very, 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 very good understanding of these results. These In fact, he has helped a lot of in a lot of races where he has helped these simulations, and those teams they won the races also. It's that important, where you can see the application also. Now, in this particular contour, or this in particular snapshot, what we can say is this is a high pressure area over here, because the car is moving and there is a high pressure area in front of cyclists. Now, the thing is, if the closeness between the cyclist and the car is very minimum, okay, now this high pressure area is what? Pushing, okay, and behind the cyclist, what is the pressure? Low pressure area, because of course it is because of the flow separation. Now the flow will go from high pressure to low pressure. That will affect the performance of cyclists. And you might have seen in some races, there are always sidecars which are running with cyclists, or if there is a marathon, in fact, there are some vehicles. Those vehicles, they can affect the performance of the cyclist. And these kind of races, every single second matters. Every single second matters. Their performance, the way they ride the cycle, you see the posture, it is aerodynamic posture. And the wheel, it has only 3 spokes. The rear wheel is in fact fully covered. So these are the different areas. It's not just the aerodynamics where you can study. It's not just one place where you can study, but there are a lot of areas where the performance matters. In F1, every single split matters when you're going for a lap time. That lap time, if you see, if somebody is following the F1, you see always come into the seconds, and that winner is decided into the split of 1 second. If you are a loser, you are a loser. Once, if that 1 second can decide the result of races. So the physics, the flow, the understanding of those things are that much important. Computational fluid dynamics is not just a tool to do simulation meshing. No, those are the parts. Those are the process you have to do. But how much actually you understand the physics, where you are applying those physics, all those principles, for what benefit, for what if somebody the drag coefficient, I remember in my past, in my previous industry, where we have achieved the drag coefficient, it was improved by 0.5%, which was very big, which was very big achievement, at least when we are trying for a lot of things and we were not able to achieve. So 0.5, you understand, 0.5 is really small, but when you're calculating the drag, when we are doing studies, that 0.5% is really big, very big for the improvement. Now let's see the module 3, where we'll be talking about the challenges in CFD. What are the challenges? Okay, so let's talk about automobile, which is standing over here, and there are different fields. Now when I was dealing with the aerothermal simulations, I used to deal with the aerothermal simulation where you have to compromise, not compromise, where you have to establish everything very carefully. uh, you have to have a good aerodynamic design, okay, for the less fuel consumption, and you have to have a good flow around the car, in fact the underbody, so that the parts, or the any parts which is near the exhaust should not get heated up. So it's between a fight in the flow and thermal, where you want minimum flow so that the drag should be less, but you want maximum flow so that the cooling should happen. So it's like two opposite forces where you have to make a combination, or you need to, make establishment where both are good. So dealing with those factors where one is not independent of other, where it's, the really challenging, where you are seeing the impacts. Okay, if you have, if let's take an example of where you have, good aerodynamic design that will directly correlate the wind noise, because wind noise is something, because the flow is, the air is interacting with the truck. So of course the friction or the flow separation, it will create a noise also. Then the vibrations, if the flow separation is too much, that can cause the vibration also. That's very much possible. Crosswind, for the fluid sorry, the flow the fuel consumption, the headlight cooling, the stability, and more. So these are the places where you can see it's not straightforward when you're actually going for the product development. It's not that straightforward. Aerodynamics, if we think it's a simple just to make a sleek design, no, not at all. It's way more complex. It's much more complex. If you want to understand how complex it is, try to reduce the drag coefficient of vehicle from the underhood. We have engine, we have a lot of parts, and even if you're able to achieve 1% of that, that's really great. 10%, it's huge. uh, Aerodynamic doesn't just deal with the, the aesthetics of the vehicle. It's not just the look of vehicle. Yes, of course, the most important part is optimized design for the best performance, but it's not that simple. The vehicle development, keeping everything ready, the fuel consumption, all the parts should be working properly. All the parts should be, in the cooled range. They should not heat up, because heating any part, man, can, the damage, it can cause a short circuit, it can cause a fire also. So dealing all those things for the development, or if we just talk about the computational fluid dynamics, if we see, manage the, the establishment between the thermal and the flow, it's not that easy. Especially for the underhood cooling, it's not that easy. Thermal management of vehicle is not that easy. So what we get is the optimized design, which is that everyone is happy, not very happy, but okay, I'm happy with this thing, because I need to take care of other, I need to take care of my neighbor also, so that he cannot get upset. So it's okay, he is happy, I'm happy, both are in, the safe range, the vehicle performance is good. That's the aim of the development. Okay, now the challenges in CFD could be, see, now we are seeing the, product development time has changed. If you see about the industries and the competition, most of the industries, nowadays they compromise with the cost, time, and the real physics. That's how we see, because of the lot of, the assumptions. So the challenges in CFD, what can be done is to speed up the process, where you don't have to wait for much for the results. And still, I remember when I run one vehicle simulation, it takes 18 to 20 hours for a full vehicle, which is really high. Still, 18 to 20 hours is really high. So till that time, I need to understand, what type of physics, or if something goes wrong, again, I need to spend the 20 hours. Automation process, if something is wrong, why can't we just do the update on that? Why we need to run the whole simulation again? That's the one thing I am really interested into. The real physics, again, it's far more complex and unpredictable. We were talking about this along almost like, since it's starting. So uh, why we cannot get the exact solution? In fact, there is a method which is called direct numerical simulation. What we see here is DNS and RANS. I did not give any introduction to these things, because they are way more complex, and they're basically the schemes, or the solver settings, solvers. But what I can say is, one is that, which is calculating for the exact solution, and one is taking the approximate solution. We always go for the approximate solution, because this is fast, and this is way more complex, and it is not able to handle the complex geometry. The complex geometry means not just the vehicle. It's not at all. For DNS is so far very good for the simple geometry, and it takes a lot of time and effort. So we are still working on approximate solution, not exact solution. The product development time will reduce, the effort will reduce, the maybe the testing time for the physical testing will also reduce if we can work on the exact solution instead of approximate solution. Now, but of course, introducing more variables in the approximate solution, it might increase the complexity. You might be able to get something different than what we're expecting. Now, something very important is the real-time simulation. A lot of companies, a lot of firms are still working on this. This will be a game changer, really. If you can, the biggest challenge, the birth of computational fluid dynamics is the flow which we are not able to see, the fluid movement which we are not able to see from our naked eyes. If you can, if any industry can do where you can, just bring your tablet, just bring your system, and you can see how the flow is happening, that will be a great achievement of for the computational fluid dynamics. But that's not that simple as we see in the movies, as we see in the sci-fi or fantasy movies. It's not that simple. It's way much more complex than we think. Now, the thing is, what type of jobs or what type of, the opportunities you're looking for if you have a CFD skill, if you do a course, if you do a degree. The basic or the first most important part is the meshing. I'm not involving the CAD because that's the designing part, that you're not dealing with the CAD when you're a CFD engineer. If you have a CFD profile, in fact, you directly start with the modeling. That's the most basic job profile, where you'll be getting the, as per the domain, you'll be getting the geometries where you need to pre-process it, you need to establish the case, you need to set up the case for the pre-processing. That's one part. Full-fledged could be your work as an application engineer, where you are domain specific, like I am dealing with the automotive industry. So I don't do the meshing. I deal with the simulations. I see the results and I try to understand the reports and recommend the results. Other thing is, if you are interested into the development part, if you have a good grip on the coding, you can work on the GUI also. Maybe the solver development, the post-processing development, so testing, validation, and development of the tool also is involved. Research, there are basically two types of research which is based. You're doing a research on the CFD solver, existing method or new methods, or what you're doing is you're taking CFD as a tool and you're doing a research on a product. So basically you're doing a research on the betterment of the product, or you want to make tool better. The future challenge. Now, this is something which is, I would say, the challenge for the industries, for the people also. Now, the product competition, you have seen every automobile company, they're launching 1, 2, 3, 4, 5 cars per year. So of course the product competition, it's not just car, if you talk about the other technologies also. So that's one thing, product competition. The development cost and time should be reduced. The time, like I said, I still need to wait for 20 hours to get the simulation. So that can be fast enough. And development cost, one more thing is involved, is the computational power. You need the CPUs, you need the the good machines. It's not at all, it's not like CFD is very the light software, they're really heavy and they need very very good the computational sources also, the high end system, the high RAM of the system. Now, some of the areas where recently the CFD started working is on the nano and macro technologies also, where we try to simulate, where we try to understand at the nano level or the macro level how that can be changed. In the medical field, recently they started, the best example is the COVID research. I have seen how people are sneezing if they have mask, if they don't have mask, how the ventilation system should be if if there is a COVID-19 situation, or if there is any kind of such situation which is the spread can happen. So I've seen these studies doing into the ventilation of the buildings, ventilation of the hospitals. And also recently I started seeing that where the fluid dynamics is collaborated with the structure, and they're doing the simulation of heart, how much the stress on the heart is coming when the fluid is, when the blood is pumped into the heart. So it's really good where medical, where CFD can help in the medical field also, where the human structure, human body is really complex. So and we have a web of veins and the blood. So if some the combination or the collaboration with the medical happens, it's really a good research area where a lot of potential or a lot of scope is there. Still there are a lot of disease which are not curable, so which the doctors need a lot of practice. So that can be understood with the help of computational fluid dynamics, nuclear power, of course, combustion, and the resources, renewable resources. Of course, the best example is the electric vehicles. Now we are seeing in last 1 decade, I guess, we have a lot of electric vehicles. Last week Ola has came up with the Ola scooter to break the stereotype market. And main thing what you see in the electric vehicles is, of course, the lithium battery, but not batteries, but just not batteries, because engine is not there, the powertrain is not there. So there are a lot of design changes in the vehicle, any vehicle, two-wheeler or four-wheeler. In fact, now there is a research going on the industries where we can have the aircraft which are electric. So in that case, see, when we have a fuel, if we have a fuel, we can increase or decrease whatever is related to. But when we are switching the resource of power, we need to have a lot of reliability. We need to have a lot of validation study on that. So overall, if we see the computational course or computational, what I would say, the degree, or I mean I'm not saying degree or anything, but understanding of computational fluid dynamics from the product development, for the research of the product or maybe the tool itself. It has a lot of potential. And of course, the CFD is computational fluid dynamics is the industry where it's very narrow. It's in fact very, very narrow. It's not easy to get the right job. It's not easy because the computational cost is high. The physics, what you're dealing is, you need to be expert. You cannot just it's not about just pre-processing and solving the equations. It's not like that. There are a lot of research you need to understand, predict the results, do the overthinking, and not overthinking, out of box thinking. And overall, it makes a good decision to take this course because it will make you different. But the thing is, how you're going to make yourself different. Now that thing is to understand everything properly, to understand everything, the physics properly, to understand the tool tool properties, and tool properly inside out, what is expected. So that way you can make a career, maybe in the research field, maybe as an application engineer, maybe a developer.